Chapter 6 Phase Diagrams for Mixtures. In this chapter, we are going to learn phase diagrams for mixtures. This includes liquid-vapor phase diagram, liquid-liquid phase diagram, liquid-solid phase diagram, and the cooling curves. If you took organic chemistry, you may remember the distillation experiment. Distillation is a common technique to separate molecules based on their boiling point. An example is a mixture of diethyl ether and toluene. These two molecules may be separated by distillation because one has a low boiling point, one has a higher boiling point. So here is a setup for simple distillation. A round bottom flask contains a solution of A and B. In the solution phase, the mole fraction of AB are labeled by XA, XB. When the solution is heated until it boils, some of the molecules start to vaporize. So in the gas phase, the mole fraction of AB are labeled by YA, YB. So here are some questions we want to answer. For both A and B, are their mole fractions in the liquid phase equal to the mole fraction in the gas phase? If not, which one is greater? Second question, what is the boiling point for the solution? To answer the first question, we realize that many molecules have different boiling point, and that indicates they have different volatility. The molecules that has a lower boiling point indicates they are easier to vaporize, so they are more volatile. Okay, so assume we have a solution with 50% of A and 50% of B. When they heat it, okay, when you heat the solution, it starts to vaporize, and assume A is more volatile, has a low boiling point, then in the gas phase, we may expect more A in the gas phase. So let's say 90% of A in the gas phase. Why? Because A is more volatile, so it goes more to the gas phase than B. So in the gas phase, we may only have 10% of B. Okay, so that indicates that the component, okay, that is more volatile should have higher mole fraction in the gas phase than the liquid phase. On the other hand, for the less volatile components, it stays more in the liquid phase than in the gas phase. So XB is greater than YB. Now what about the boiling point? Okay, we're going to show you later that the boiling point depends on the concentration. So when you make a different concentration liquid, the boiling point changes. Now before we introduce the phase diagram, we want to look at how these parameters change, related: temperature, pressure, mole fraction in the liquid phase, mole fraction in the gas phase. In the last slide, we showed that there are many parameters to consider before we draw the phase diagram for more than one components. They are temperature, pressure, composition in the liquid phase, composition in the gas phase. Now these parameters are not all independent. They are related by an equation called the phase rule. So this slide, we're going to derive this phase rule. All right. Now suppose P is the number of phases, C is the number of components, F is the number of degree of freedom. Let's take pure substance as an example. All right. So pure substance, single phase. Suppose you have two phases in equilibrium, liquid and the vapor phase. All right. So in this case, the P is the number of phases is 2, okay, liquid and vapor, and C is the number of components is 1. It's a pure substance, single component. Okay, but what is the number of degree of freedom? What parameters we can change? We may change temperature, we may change pressure, but in chapter 4 we learned that when two phases are in equilibrium, temperature, pressure are related by Clausius-Clapeyron equation. And that means we can only change one of them. If we change temperature, the vapor pressure will follow the equation. Okay, so there's only 1 degree of freedom. So F equals 1 in this case. What about a two-component system? So if you have a mixture of A, B, so in the liquid you have XA, XB, and if this liquid in equilibrium with the gas phase, you have YA, YB. And therefore, we have number of phase is 2, still have liquid vapor phase. Components, you also have 2, A and B. But what is the number of degree of freedom? This is the one we need to find out. Okay, so in this case, the total number of variables that can change are temperature, pressure, mole fraction AB in the liquid phase, mole fraction AB in the gas phase. Total is 6. Are they independent? Well, there are mathematical equations related to them, and the two simple equations are mole fraction in the liquid phase add together is 1, mole fraction in the gas phase add together is 1. Okay, whenever you have a mathematical equation, you need to minus one of the variables because there's only one you can change. You can change mole fraction B, the mole fraction A can be calculated. It follows the equation. So in this case, 6, you need to minus 2, give you 4. So 4 variables that you can change by considering these two equations. Now in general, the number of equations relates these mole fractions can be calculated by number of phases, number of components minus 1, the product, plus 2. So in this case, number of 2 phases times number of components, 2 minus 1, plus 2, that give you 4. So 4 variables that may change. So are these 4 variables completely independent? The answer is no. There are more equations to relate them. So because the phases are in equilibrium, their chemical potentials must be the same. So in this case, you have 2 more equations. One is for A, the chemical potential in the liquid equals chemical potential in the gas phase. And there's another one for B. And therefore, you have 2 more equations. So 4 minus 2 give you 2. And therefore, you have 2 independent variables that can change for 2 components, 2 phases system. Okay, compared to the single component, pure substance, you only have 1 degree of freedom. Here you have 2. You can change temperature. You can also change pressure. But then the number of moles in the liquid, mole fraction in the liquid phase, in the gas phase cannot be changed. All right. So 2 degree of freedom for this system is 2. Now, in general, the number of constraints relates the chemical potentials can be calculated by the number of components times phases minus 1. Okay, and therefore the number of degree of freedom can be calculated by this equation. So here P times C minus 1 plus 2, that's the number of variables after considering the mole fraction added together is 1. And then you minus constraints due to the chemical potentials. So by doing that, we have the final phase rule, that is the number of freedom equals number of components minus number of phases plus 2. So let's calculate 2 components, 2 phases system. So 2 minus 2 plus 2, that gives you 2. Again, you have 2 degree of freedom. Let's see how we can use this phase rule. We first look at a pure substance, and this shows a pure substance phase diagram. So any point in one phase region, for example, solid phase, okay, the component is 1 because it's a pure substance. The phase is also 1 because you only have one single phase, that's the solid phase. And the number of degree of freedom is 1 minus 1 plus 2, that gives you 2. So you have 2 degree of freedom. What are they? They can be temperature and pressure. So you can change both temperature, pressure. For example, for water, -5 degree, 1 atmosphere, that's ice. you can change temperature to -6 degrees, and the pressure you can change to 2 atmosphere, and still ice. So you can change temperature, you can also change pressure, and the phase remains as a solid. Okay. Now let's look at a point on the phase boundary. For example, liquid vapor phase boundary. So how many components is still one, because a single component, pure substance, for example, water. And how many phases? You have two now, two phases in equilibrium. Then how many degree of freedom? So 1 minus 2 plus 2, and that gives you 1. You only have 1 degree of freedom that you can change. So if you want to keep liquid vapor in equilibrium, all right, you can only change temperature and the pressure will follow Clapeyron equation. Now what about the triple point? Okay, remember triple point has 3 phases in equilibrium. C is still 1, so 1 minus 3 plus 2, that gives you 0, and therefore the degree of freedom is 0. Okay, at the triple point. That means that you cannot change the degree of freedom. Temperature, pressure, for different substance, they are unique. Okay, you cannot change that, as we mentioned before. All right, no degree of freedom for a triple point. It's determined by nature. All right, what about two components system? So you have 2 phases, 2 components. So C is 2, P is 2, and then the degree of freedom is 2. So in this case, you can change both temperature and pressure. The components cannot change if temperature, pressure are fixed. The phase rule tells us that for a 2-component, 2-phase system, there are 2 degrees of freedom. Both temperature, pressure can change. To plot the phase diagram with 2 degrees of freedom is difficult. So we keep one constant and change it, only plot one variable. And so you will see 2 types of phase diagrams. One is keep temperature constant, plot the pressure as a composition phase diagram. The other is keep a pressure constant and plot temperature as a composition phase diagram. So here we are going to show first we keep a pressure constant, 1 atmosphere, and we plot temperature as a function of mole fraction. Okay, in the mole fraction ZA represents mole fraction both in the liquid phase and the gas phase. So we'll see how this works. All right. Now for a 2-component system A and B, in this phase diagram here, we plot mole fraction as A. That means when A is 0, this is B. So the left side is B and right side is A. And the temperature represents the boiling point for the pure substance. So the left side is the boiling point for pure B, and the right side is the boiling point for pure A. Now which one is more volatile, A or B? By looking at the boiling point, we can say B is more volatile because B has a low boiling point. The lower the boiling point, the easier it vaporizes, and therefore it is more volatile. So what do you expect for this system? So if you have AB liquid in equilibrium with the gas phase, and we know B is more volatile, and therefore in the gas phase, B composition should be greater than liquid phase. All right, because B is more volatile, it goes more to the gas phase. So gas composition is greater than the liquid composition. On the other hand, A will be less volatile, so it's trying to stay in the liquid phase, and therefore the YA gas phase should be less than XA. Okay, for a less volatile components, it stays in the liquid phase, so the mole fraction in the liquid is greater than in the gas phase. All right. Now suppose the temperature for these two is T. So for a certain, let's say temperature T, Okay, at this temperature, the two phases are in equilibrium. We just showed that A is less volatile, and so the mole fraction in the liquid is greater in the gas phase. So this is the liquid mole fraction, and this is the gas mole fraction for A. Okay, and that's these two are in equilibrium at the temperature T. All right. Now, if you change composition, temperature also change. So at a different composition, let's say mole fraction A is here, all right, then the mole fraction of Y is here. They are in equilibrium at another temperature. So at a different temperature, there are different compositions, mole fraction in the gas phase, liquid phase are in equilibrium. But in any event, the mole fraction of A in the liquid phase is greater than in the gas phase. So when you connect all the data, okay, you will get two curves. The bottom curve or the lower curve represents the liquid composition, and the upper curve represents the composition of the gas phase. They are in equilibrium by a horizontal line, means at the same temperature. This line is called the tear line. Okay, we're going to see more in the next slide. Here shows the temperature composition phase diagram for a two-component system. The phase diagram includes two curves. A low temperature curve represents solution composition, and a high temperature curve represents vapor phase composition. A point below the solution composition curve indicates the system exists as a single liquid phase. A point above the vapor composition curve indicates that the temperature is high enough that all liquid becomes single vapor phase. A point between the two curves indicates that the system exists as two phases, liquid and vapor phase. These two phases are connected by a horizontal line called the tear line. The tear line means these two phases are at the same temperature T. So one is liquid phase here, and the composition is XA. And the other is vapor phase here with a composition YA. Let's apply the phase diagram to a simple distillation process. On the left side, we show the phase diagram, and on the right side is a setup for simple distillation. On this phase diagram, the mole fraction is about molecule A. So when the mole fraction is 1, that means it's pure A. In this case, the boiling point of A is lower than the boiling point of B, and therefore the A molecule is more volatile, and we expect in the gas phase we have more A, and in the liquid phase we have more B. Okay, so on the right side, it shows that we start with a solution of mole fraction A equals 0.15, and therefore B should be 0.85. So this is a solution with a higher concentration of B than A. On the left side, a mole fraction of 0.15 means any point along this vertical line, okay, at a different temperature. Now, upon heating, temperature goes up until it touches the low temperature curve. That's the liquid composition curve. That's when the liquid starts to boil, and the temperature here is the boiling point for this solution of with the mole fraction 0.15. So where is the vapor phase? We draw the tear line. Okay, so the tear line means liquid vapor has the same temperature, and the vapor phase is right here. Okay, that's the vapor phase, and the composition is on the vertical line. So here is 0.7, and therefore we know the mole fraction of the vapor phase is 0.7. which is in equilibrium with the liquid composition 0.15. All right, so on the right side, we see that liquid has a composition 0.15, and the gas phase that is in equilibrium with this liquid is mole fraction 0.7. And this is consistent with what we expected, that A is more volatile, and so in the gas phase we have more A, which is 0.7, than the liquid phase, 0.15. Conversely, B is less volatile, so the mole fraction is 0.85 in the liquid and 0.3 in the gas phase. All right. Now, here in the setup, we also have a cooling system so that all the gas phase condense into the liquid phase. And so in this collection flask, the vapor phase becomes liquid. So the mole fraction now becomes XA equals 0.7. On the left side phase diagram, the vapor phase YA equals 0.7. Upon cooling, we draw the vertical line until the temperature below the low temperature curve, and that's when it becomes liquid. So any point below this liquid curve composition curve is a point with solution mole fraction XA equals 0.7. Okay, so this setup shows that by distillation, the vapor phase is collected which contains higher concentration of A. So we start with a solution with more B, all right, XA equals 0.5, and B should be 0.85. Okay, we end up with a solution with mole fraction of A 0.7. Okay, so a higher concentration of B solution, and after distillation we get a high concentration of A, and so we achieve some degree of separation. Okay, A and B are separated, but the separation is not high degree because we only get 0.7 A. All right, and in general, simple distillation cannot achieve 100% pure separation. In the last slide, we showed an example of simple distillation. We start with a solution of mole fraction A equals 0.15. After distillation, we get a vapor phase of 0.7 A. Okay, so gas phase has more A. By cooling, we get a solution of 0.7. So more B, a solution of high B concentration, and here we get a solution of high A, and we achieve some degree of separation. But the separation is not good enough because the vapor phase only have 0.7. Is there a possibility to get higher concentration? For example, we get 0.95 or even 100%. And one possibility is that after collect the liquid, okay, after cooling, okay, after cooling the vapor phase, we get a liquid 0.7, and then we use this liquid, all right, as the initial solution, and we distill this again. So let this liquid heat until it becomes boil. So the vapor phase, we draw teal line, all right, and then the gas phase should have even higher concentration from 0.7 becomes 0.95, and then we let this vapor phase cool, and then becomes a liquid and vaporize again, so you will get even higher concentration. All right, so by doing several times, we can achieve very high concentration, even approach 100% separation. We just showed that by multi-step separation, it is possible to achieve a high degree of separation. In practice, the separation is achieved by fractional distillation. In fractional distillation, we use a column that contains several plates. So here is how it works. suppose we start with a solution that has a concentration 0.2 A. All right, so in the phase diagram, it is a point that has a concentration 0.2, so that's here, at a temperature, let's say room temperature. Upon heating, the temperature go up until it touches the lower temperature curve, and that is when it starts to vaporize. So the gas phase concentration can be found by drawing the teal line, which has the T1 temperature, all right, and we find the concentration is 0.8, all right. So as we shown before, A is more volatile because it has a lower boiling point. So in the gas phase, it has a higher concentration than in the liquid phase. So now, if you look at the right side, the setup of this fractional distillation, we have a vapor phase that is above the liquid, has a concentration 0.8. And this gas phase goes up when it goes through the first plate. It starts to condense, becomes a liquid. And the liquid on the first plate has a concentration 0.8 because this comes from the gas phase. All right, so it is 0.8. And on the left side, the phase diagram, it is the vertical line from this 0.8 gas point until it touches the lower curve, and that is when it starts to become a liquid. Now, on the column, there's a temperature gradient such that the liquid on the plates also vaporize, also boils, and therefore there is a vapor phase above it that is in equilibrium with this liquid. So in the phase diagram, we again draw the teal line for the second one, liquid, which it has 0.8, and the gas phase now is 0.95, that is in equilibrium with this liquid. And so if you look at the right side, the gas phase above the first plate has a concentration 0.95, all right? And this gas will condense on the next plate, becomes a liquid, and this liquid will vaporize, and the gas phase has even higher concentration, 0.98. So if you have more plates, then you have more equilibrium between liquid and the gas phase. And in the gas phase, it becomes richer and richer in A. And so eventually on the top of the plates, you can achieve very high concentration of A. Here shows an example of fractional distillation column called bubble cap fractional column. Liquid is evaporated in the boiler, and the vapor is forced to bubble through a thin layer of boiling liquid, and the vapor produced from this liquid is richer in more volatile component, and the vapor bubbles through another layer of boiling liquid, and then the vapor becomes more richer in more volatile compound, and then it goes up, all right? And the vapor that has reached the top plate is essentially pure in the more volatile component. As we shown before, on the phase diagram, each of these horizontal lines represents a liquid vapor equilibrium, liquid vapor in equilibrium, or vaporization condensation step. So each of these horizontal line or teal line is called the theoretical plates. Now, different mixture may have different phase diagram. So if we compare these two phase diagrams, you can see the second one, the two curve, the vapor phase composition curve and the liquid composition curve are very close to each other. And to achieve the same separation, for example, first one you need to separate from 0.3 mole fraction to 0.98. Same thing is here, 0.3, 0.98. For the first phase diagram, we need 3 theoretical plates. And for the second one, we need 5 to achieve the separation, the same separation. And therefore, the number of theoretical plates are strongly affected by the shape of the two-phase liquid-vapor region in the phase diagram. And later we'll show you the presence of azeotrope is also an important factor to determine the number of theoretical plates. So far we have discussed temperature composition phase diagram. Now let's move on to the pressure composition phase diagram. But first let's go over the temperature composition phase diagram. So on this phase diagram, all right, the vertical line represents temperature, horizontal is the mole fraction. All right, so we have two curves. One is high temperature curve, one is low temperature curve. High temperature curve represents vapor phase. Low temperature curve represents liquid phase composition. And if you look at the pressure composition phase diagram, you see they look similar, but there are important differences. Again, for the temperature composition, the high temperature curve is the vapor composition curve. Any point above it is a single phase vapor phase, all right? Because high temperature favors vapor phase. But on the pressure composition phase diagram, high pressure actually favors liquid. So note that they are opposite. On the pressure composition, high pressure is liquid and high temperature is vapor phase. And low temperature is the liquid and the low pressure is the vapor phase. In between, you have two phases, just like temperature composition. So two phases, all right? And one is vapor phase, one is liquid phase. They are connected by the tear line. Same thing is here, all right? So any point in between that can separate into two phases, liquid and the vapor phase. Pressure composition phase diagram can be theoretically derived and plotted. By using Raoult's law, we can express partial pressure of A and the partial pressure of B as a function of XA, and combined together, we have total pressure as a function of XA. We can plot total pressure as a function of XA. We get a straight line, and that's one of the two curves we see in the pressure composition phase diagram. That is the pressure liquid composition line. By using Dalton's law combined with Raoult's law, eventually we can derive the equation to express the total pressure as a function of YA. Plot it, and that is the pressure vapor composition curve on the pressure composition phase diagram. In the last two slides, we derived two equations. One is the total pressure as a function of XA. This represents the pressure and the liquid composition curve. The other equation is total pressure as a function of YA. This represents the pressure and the composition of the vapor phase. Assemble these two together, we have the pressure composition phase diagram. Here is an example of interpretation of the phase diagram. And let's start at point A, because point A is at a high pressure liquid phase region, and we can say initially we only have a liquid phase. Now, the liquid phase remains as a liquid phase before it reaches pressure P1. So at P1, pressure P1 or point A1, the pressure is low enough that the liquid starts to vaporize. So you have two phases, and the vapor phase can be found by draw the tear line to be at A1 prime. So when you lower the pressure further, before it reaches P3, you always see two phases. Okay, so the two phases, one is a liquid, one is a vapor phase, liquid and vapor phase, until the pressure is low enough to below P3. So for example, at A4, then all liquid vaporized becomes a single vapor phase. On a phase diagram, if liquid vapor are in equilibrium, we can find the mole fraction in the gas phase and the liquid phase by drawing the tear line. But how do we find the amount of substance goes to the liquid and the vapor phase? Suppose we make a mixture A plus B, and we know the number of moles A, number of moles B, so we know the mole fraction. So let's say ZA is the mole fraction that we made the mixture. Okay, now under certain temperature pressure, this system falls in between the two curves, the two composition curves. That indicates this system will separate into two phases. One is the liquid phase, one is the vapor phase. And by drawing the tear line, we find the mole fraction of the gas phase and the liquid phase. And we know the total number of moles because we know Na and B. Okay, so total number of moles, okay, how much added, we also know that. All right, but how many number of moles in the vapor phase and how many moles in the gas phase? And that's the amount of substance we want to find out. Okay, now, this is described by the level rule. Okay, the level rule can be easily derived by using mass conservation. And if you are interested, you go to the textbook and we'll find the derivation. But here we'll skip the steps and give you the results. And the results is that the number of moles in the liquid phase times ZA minus XA. ZA is the mole fraction you initially made. So that's here. Okay, when you make this mixture, all right, that's the you can call it the total composition. But then it separates into two composition. So ZA minus XA, XA is the mole fraction in the liquid phase. So when you use ZA minus the XA, that is the length here, which is called NL. LL, sorry, it's LL. That's the liquid length, all right, because it goes to the liquid composition line, all right. And then equals NV, so NV is number of moles in the gas phase times YV, okay, YA, so YA is the mole fraction in the gas phase is here minus initial total composition. So that is YA minus ZA, and that is the length towards the vapor composition curve. So that's called LV. All right. So again, it's NL times LL equals NV times LV. Okay. Now using this equation, we can calculate the ratio of amount of substance in the liquid and in the vapor phase should equals to LV divided by L. So LV, LL can be measured from the this phase diagram, and then we can calculate the ratio of amount in the liquid in the vapor phase. Now, in order to find exactly what is number of moles in the liquid and in the gas phase, then we need one more equation. All right, so the equation is Na plus NL or NB. That's how much we added. That's the total number of moles total. Okay, so so that give you if you know the total number of moles, which is also equals to NV plus NL. Okay, so how many goes to liquid, how many goes to the vapor added together is the total number of moles. So by using this equation plus the level rule, you can calculate the exact amount goes to liquid and goes to the gas phase. And we're going to see some examples later. The phase diagram we discussed so far are for ideal solution or the solution close to ideal. Let's assume you have a mixture AB. Right? A is on the right side, B on the left side. The boiling point of A is lower than B, and for a mixture, upon heating, temperature go up until it touches the liquid composition curve. It start to boil, and you do the tear line. You draw the tear line, and you get vapor phase, and the temperature here is the boiling point of this mixture. The boiling point here is higher than A, boiling point lower than B. In other words, the boiling point of a mixture is always between the boiling points of the two pure substances. When the solution are non-ideal, then the phase diagram may look very different. For example, on the left side here, we show a phase diagram with maximum boiling point, and on the right side, a phase diagram display a minimum. The mixture at the maximum minimum is called azeotrope. The composition of the liquid and the vapor phase is the same as this azeotrope. Let's take the left phase diagram as an example. Suppose we have a mixture, all right, at the azeotrope composition. So upon heating, temperature go up until it touches the liquid composition curve. It starts to boil. But since we only have one point, a maximum point, so when you draw tear line, it's still at this point. That means that the vapor composition equals the liquid composition. No separation can be achieved by distillation because the vapor phase has the same composition as the liquid phase. And the azeotrope is also called constant boiling point mixture. The origin of azeotropes is the deviation from ideal solution. Suppose we have a mixture of AB, and there are intermolecular interactions between A and A molecule, B and the B molecule, A and the B molecule. Upon heating, the molecules gain kinetic energy, and when the temperature is high enough, the molecules gain enough kinetic energy that they can escape from the intermolecular interaction and becomes a gas phase. And that's when the solution start to boil. Okay, so let's look at the first phase diagram. All right, on the right side is pure A, so you have intermolecular interaction A, and this is the temperature when the molecules has enough kinetic energy to escape from the interaction, becomes gas phase. And on the left side, that's the pure B, so you have B intermolecular interaction, and the interaction is stronger, so you need a higher energy, okay, higher temperature to escape, becomes gas phase. The boiling point of B is higher than A. Now, why you have a azeotrope that has a maximum boiling point? Well, that indicates that A and the B intermolecular interaction is strongly attractive. All right, so that you need even higher temperature to break apart the intermolecular interaction and becomes gas phase. And example include trichloromethane propanol mixture or nitric acid water mixture. On the other hand, on the right side phase diagram, we see a minimum boiling point azeotrope, and that indicates the A and the B intermolecular interaction is strongly repulsive, and therefore you need a low temperature to break apart intermolecular interaction and becomes gas phase. Examples include dioxane water and ethanol water mixtures. the existence of azeotrope has important consequence on fractional distillation. Let's go over fractional distillation on a normal phase diagram. So here we have A and B mixture. So A has a low boiling point than B, so A is more volatile. Okay, so now a mixture is heated, it starts to boil, and draw tear line, and the vapor phase is here, which has a higher concentration of A, all right, in the gas phase, because A is more volatile. And then the gas phase condenses at the first plate and becomes a liquid, and the liquid vaporizes with a vapor phase has even higher concentration, and then the gas phase condenses on the second plate, so it repeats itself, and if we have enough plate and on the top the concentration approach pure A. Okay, that's what happens for a normal phase diagram. Now what happens for a phase diagram with a azeotrope? Okay, we start with a liquid A, A1, so the mole fraction is XA, and when heated, it starts to boil at this point, so the temperature is T1, and the vapor phase is A1 prime, which has a higher concentration of A. So these are similar to the normal phase diagram, and the phase vapor phase condense and becomes A2, a liquid. Here is the liquid, and the liquid start to vaporize at the first plate. Okay, and the vapor phase is A2 prime, and the A2 prime condense at the next plate, becomes a liquid A3. Okay, so then A3, the vaporize becomes gas phase A3 prime. So you repeat this step. Now here is the difference. No matter how many plates you have, you cannot pass the azeotrope point. So because there's a point here that the maximum you can get is approach this point. Okay, in other words, the vapor at the top plate reaches azeotrope, but not beyond. Okay, so if you have a mixture you want to do fractional distillation, all right, on the top of the fractional distillation tower, the maximum you can get is not pure A or B, it's the azeotrope. Okay, if you start from right side, let's say A10, all right, and the vapor phase is here, okay, condense, so eventually you still get the azeotrope. The phase diagram we talk about so far are liquid vapor phase diagram. Some liquid, they are partially miscible at a low temperature. So here we're going to show you liquid-liquid phase diagram. For example, nitrobenzene, hexane are partially miscible. So here is the phase diagram, and on the curve there's a maximum temperature. This temperature is called upper critical solution temperature. Above this temperature, two liquid combined forms a single liquid. So if you have A-B mixture, you only see one phase above the upper critical temperature. Now below this temperature, however, for example, if the point fall in here, then it will separate into two phases. So it goes to two liquids. So one we call phase 1 or alpha phase. The other we call phase 2 and we call beta phase. And in the phase diagram, one is on the left side and one is on the right side by draw the tear line. So you can call this phase 1, phase 2, or alpha, beta. The composition of the two phases can be found when you draw vertical line. So for example, here is 0.3 and here is 0.8. all right, B. Okay, mole fraction B is 0.3, 0.8. So that means that in the beaker, one is mainly A. So this is the majority is A, 70% A. And on the bottom is 80% of B. So you separate into two phases, all right, two liquids. They are partially miscible. And the amount, so how many number of moles in alpha, how many in beta, the relative abundance will be found by the level rule. We'll see in the next slide. Simple question. A mixture of 50 grams of hexane, 50 grams nitrobenzene was prepared at 290 Kelvin. What are the composition of the phases, and in what proportion do they occur? To what temperature must the sample be heated in order to obtain a single phase? So here is the phase diagram, and this phase diagram, the mole fraction is about nitrobenzene. So first thing we need to do is calculate the mole fraction of nitrobenzene using grams. Grams, you calculate the moles, okay, divide by molar mass, and grams calculate the moles. From the 2 moles, you calculate mole fraction. So the calculated mole fraction for nitrobenzene is 0.41. And then you go to the phase diagram. So you find 0.41 and the temperature 290 Kelvin. Combined together, we find the initial point, which falls inside the curve. That indicates this will separate, the system will separate into 2 phases. So we call them alpha and the beta, okay? And the alpha phase, we draw the vertical line, find the composition is about 0.35. So let's say this is 0.35, and the beta is about 0.83. Okay, so the question now is, in what proportion do they occur? And that we need to use the level rule. So n alpha, all right, times L alpha, n beta. So n alpha. So this is the n alpha times L alpha, n beta times L beta, and therefore we have the ratio n alpha n beta equals beta L beta L alpha. So L beta is this length, which can be calculated by 0.83 minus 0.41. All right, that's this one. And the L alpha is 0.41 minus 0.35. So the answer is 7. All right, so you have more molecules go through the beta alpha phase. Okay, 7 times in the alpha phase than in the beta phase. We just showed that some liquid are partially miscible at low temperature, and here is the phase diagram at low temperature for the partially miscible liquids. When the temperature above the upper critical temperature, 2 liquids merge into one single liquid. And if temperature is high enough, then the liquid may vaporize. So you have 2 phases. So this phase diagram combines the liquid vapor phase diagram that we already seen. And in this case, we have azeotrope here, we have upper critical temperature. So now let's start with point A1. So based on this phase diagram, A1 is a single liquid. All right. So at A1, 2 liquids completely miscible. When you increase temperature, all right, the liquid still remains as a single liquid until it touches this line, and it starts to boil. And the vapor phase is B1. So B1 is the vapor phase in equilibrium with this liquid. And when you condense it, the vapor phase becomes a liquid to B2. So at B2 you have a single phase liquid. If you cool down further, this liquid becomes two liquids at B3. Here is another phase diagram for partial miscible liquid. At a low temperature, you also see two liquids. They are partially miscible. And however, this phase diagram, when you heat it, before they merge into a single liquid phase, they actually vaporize. So you see the vapor phase. Okay, so in this phase diagram, no upper critical solution temperature is observed. Okay, so if you start with A1, all right, just like previous slides, you see a single liquid phase, and upon heating, temperature go up, and A2 is when it boils, and B1 is the vapor. When you cool down to B3, you see two phases, B1 prime, B3 double prime. Now, if you start with E1, okay, at the beginning you see two phases, B3 prime, B3 double prime, so two liquids. All right. When you heat it, all right, it remains as two liquids until at E1 or E2, sorry. At E2, now you actually see three phases. You still see some of the liquid. Let's say this is alpha phase, and another liquid beta phase, but you also start to see vapor phase. So three phases in equilibrium. Above this temperature, for example, E3, all liquids vaporize. So you only see the vapor phase. Sample question. Here we show a phase diagram that is a combination of liquid vapor phase diagram. The question number 1 is, indicate what phases are present in each region of the phase diagram. So high temperature, single vapor phase. And then you have liquid vapor, two phases. And below the liquid composition curve, you should see a liquid, okay? This is a single liquid. But inside the liquid phase diagram curve, you should see two liquids. The liquid is partially miscible in this region. Okay, it's separated into two phases. That's question number 1. Question number 2, describe the change that occur when a mixture of composition X equals 0.1 is boiled. So 0.1 is here, and assume it is at room temperature, so the initial point is right here. And when you heat it, temperature go up until temperature become about 330. All right, it start to boil, and the vapor phase can be found by the teal line. And here is the vapor phase, and the composition is about 0.34. Okay, now assume when you condense the liquid, the vapor phase becomes liquid at room temperature. So that will be in this point. And because this again is inside the liquid composition curve, so you should see two phases. We draw the teal line. Okay, the left side we can call it phase 1 or alpha phase. The right side we can call it phase 2 or beta phase. Okay, the composition, you draw the vertical line, and you will find one is 0.17, one is 0.088. Okay, the relative amount in the phase 1, phase 2. So let's say this is phase 1. All right, N1. This is N2. So the amount goes to 1 and 2 should obey the level rule. So N1 times L1, N2 times L2 should equal. And the ratio can be calculated by the length of L2 divided by L1, and that gives you 3.18. Indicates that more number of moles goes to the the left side, the phase 1. Okay, so question number 3. Suppose the mixture in question 2 is allowed to boil to dryness in an open container. What would be the final temperature? Okay, so we start with 0.1, and here is when it starts to boil, and this is the first vapor phase composition. And you can see the vapor phase has more A in it than B. And in other words, more A escape from the liquid. So the liquid should have more B with time. Initially 0.1, after 5 minutes maybe it goes to here 0.08, all right, because A already escaped, more A escaped. So you have less concentration of A, and with time it just approach to the left side until it becomes almost B, pure B, and the temperature is 360. So the answer is final temperature should be 360. The next question is, suppose all vapor produced in question 3 was collected and condensed. All right, all vapor, so all the solution vaporized becomes vapor and you condense it. And so the concentration should be the same as the initial liquid composition. So the answer is that the composition of the resulting liquid should be 0.1. All right. Next question. If you fractional distill a mixture with an initial composition 0.9, so 0.9 is here, and when you heat it, and this is the point when it vaporizes, and the vapor phase, you draw teal line, and then you let it cool. But because we have azeotrope, so as we learned that the maximum concentration you can get on the top of the distillation tower should equal to the concentration of azeotrope, and so the answer is 0.53. Here shows the liquid-solid phase diagram. This phase diagram resembles the diagram for partial miscible liquid that boils before completely miscible. You have seen those phase diagrams in the last 2 slides. And at high temperature, the mixture forms completely miscible liquid. At lower temperature, one of the solids freezes first, and eventually both will freeze, becomes 2 solids. For example, on the right side, any point here represents 2 phases. When we draw the teal line, the left curve indicates it's a liquid. On the right side, it's a solid B. Okay, so that means at this point, solid B freezes first. All A remains in the solution. Some B still remains in the solution, but some B freeze out. Okay. Now on the left side, for example, point here, the 2 phases. One is the liquid phase mixture, the other is the solid A. So that means A freeze at this point. A freeze out first. All right, but still some A remains as a solution. At a very low temperature, for example, here there's no liquid, only 2 solid. So you draw teal line, solid A and solid B. That's all. Okay. So now let's assume we start with point A, A1. What do we see? It's a liquid. It's a completely soluble liquid. When the liquid cools down until A2, at this point, what do we see? Okay, we see the B start to freeze out. So we see some solid B in the solution. All right, that's what we see at A2. Now, if you cool down to A3, all right, you draw the teal line, you still see some liquid mixture and some B freeze out. So when the temperature goes down, you always see 2 phases, a mixture, liquid mixture, and the solid B. But when the temperature goes down, more and more B comes out, all right, and the less and B remains in the solution until point 4. Okay, what do you see now? Well, not only B comes out, A also come out. All right, so now you see 3 phases: solid A, solid B, and a liquid solution. If temperature goes down further, for example, let's go to A5, what do you see? All liquid disappear because they all freeze. And now you only have 2 solids, solid A and solid B. All right. Now, if you go to the left side, let's say you start with point B, what happens? Okay, B1, what happens? It's still a completely soluble liquid. And when you cool down this until, let's say this is B2, and now you see A start to freeze out. So in this point, A freezes out first. When you cool down, you always see two phases, liquid, mixture, and solid B. So more and more B comes out of the solution until at this point you see three phases, solid A, B start to freeze out too, and some liquid remains. Okay, so three phases. Below this temperature, then only two solids. Okay, so that's when solid freeze. But if you go to the opposite direction, let's say you start at this point, okay, that's two solids, okay, and if you heat it, all right, at this point, you see three phases, and that means solid A, solid B, and some liquid. In other words, it starts to melt. So this is the starting melting point, okay? And when you heat it further, you always see solid remains, but more solid becomes liquid. And therefore, until this point, all right, all solid becomes liquid. So in other words, all this range are the melting point. The melting point is a range because along all this temperature, you always see some solid remains, more liquid start to melt, all right, until in the end here, all liquid becomes, solid becomes liquid. So you have a range of melting points. Now point E here is a special point. It's called eutectic composition. So this is the mixture with lowest melting point, and the solid melt without changing its composition. For example, if you start at this point with the eutectic composition, when you heat it, okay, heat it until the melting point it starts to melt, and then immediately becomes liquid. All right, so the melting point is very sharp. All right, not a range, but a sharp range, a sharp melting point. All the solid will melt immediately, becomes liquid. Here shows a phase diagram for a reacting system. You may notice that this phase diagram contains two of the solid-liquid phase diagrams we saw in the last two slides. Indeed, and this is because when A and B combine, they form a product. So A, B forms product, A, B combined. That's a product, or you can write it as a C. Now this product only stable up to melting point. In other words, if temperature is too high, it doesn't exist. It goes back to A and B. And so at high temperature, you only see liquid phase, A and B mixture. Okay, and at a very low temperature on the left side, you have two phases. Okay, this is the product. So this line is AB, the product. Okay, or sometimes we just write C. All right, on the left side is A. So you see two solid, solid A, solid AB. All right, and the right side is solid B, solid AB. Okay, and here, any point here, all right, solid A, that's solid A, and the solution of A and B. Okay, any point here, all right, you see again liquid mixture of AB with product AB. Similarly, any point here, all right, represents a liquid solution with product AB. Any point here, you have solid B and the mixture solution of AB. Notice that we have two eutectic composition. So these two composition, one is for the product AB and B, and the other is for product AB and A. Here shows the solid-liquid phase diagram for potassium-sodium mixture, and this mixture forms a solid product, sodium-potassium, at low temperature. This product is not stable and decomposes at this point to form solid sodium and a molten salt solution. This kind of melting is called incongruent melting, compared to the congruent melting we saw in the last slide. In this slide, we introduce cooling curve. A cooling curve is a plot of how temperature change with time as for phase transition. So the left side is a solid liquid phase diagram for AB mixture. Here is A, here is B. All right. Now let's start with a point B5. B5 is a liquid. Upon cooling, temperature goes down until B4. So from B5 to B4, it's a liquid cooling. Temperature goes down. All right. At B4, A start to freeze. Okay. So this point, A freeze. When A freeze, it release heat. Okay. Imagine water. Okay. When ice melt into water, it absorbs heat. So we all know ice need to absorb heat to become water. So the opposite process, water freeze, release heat to the surrounding. So at B4, when A freeze, it release heat. And when heat is released, it slows down the cooling process. And therefore, you see a cooling line that has a different slope, a smaller slope. Okay, so the cooling becomes slower. It needs more time to change temperature. Okay. Now, so this is different from a pure substance. So again, think about water. So when water cools down, you see a straight line. So this is water cooling. All right, until 0 degree. At 0 degree, all water becomes liquid, becomes solid ice. So you see a flat line, okay? Because again, water freeze, release heat until all water becomes ice at 0 degree, and then ice cool. So this is ice cooling. All right, different slope. All right, so you see a flat line. But if a mixture, you don't see a flat line when A start to freeze. You see a cooling with a different slope until B2. Okay, what happens is at B2, now all liquid freeze becomes two solid, solid A, solid B, and so you see a flat line. All right, this is called eutectic hot. Now so at eutectic hot, all liquid becomes solid, and then two solid freeze, two solid cools down. So again, a different slope. Now this shape, the cooling curve shape, depends on the location. So if you start at this point, let's say this is point A, then from A until B3, all right, that's the liquid. So on the cooling curve, you see a longer line, all right, that's a liquid cooling. Until B3, A start to freeze, and so the slope change, all right. So from A3 until this point, let's say this is A4, all right, and you have a different slope on the cooling curve. Now, because A3 to A4 is a short line, that means only a small amount of A freeze, and therefore there's more A remains in the solution, and therefore you see a longer eutectic hot because you need more time to freeze A and B becomes solid. Okay, and then solid cooling here. All right, now if you start at this point, that's the eutectic composition, then you see a long eutectic, the liquid cooling, all right, and the long eutectic hot. Okay, both liquid, all the liquid freeze becomes too solid, and then the solid cooling. And this cooling for eutectic composition resembles the pure substance cooling process.